morning students, welcome back to our next class. Today I would like to explain examples of inner product spaces and Hilbert spaces. So here you have many examples, but in that I will explain only two examples with proofs. That two examples are very important for short answer questions. So the first one is the Euclidean space R power n is a Hilbert space. Second one is the unitary space C power n is example of Hilbert space having the proofs also. So now I would like to start our first example, Euclidean space. Okay now? See our first example. The Euclidean space denoted with R power n is Hilbert space. So it compulsory satisfies all the Hilbert space conditions. We will show that the proof also with an inner product defined by inner product of two vectors x comma y is equal to x1 y1 plus x2 y2 so on xn yn, where x is equal to R power n, so that ordered of n tuples, y is equal to ordered of n tuples. Then inner product of square root inner product of x comma x value is given, root of x1 square plus x2 square so on xn square, nothing but a norm x. And from this we obtain the Euclidean metric d of x comma y also, that is it, that equal to norm x minus 5 is equal to root of inner product x minus 5 comma x minus 5. Okay, using these conditions, inner product of two variables in the R power n is this thing, and variables are like this, and root of inner product x comma y is root of inner product x comma x is equal to this thing. Using all these conditions, we have to show that this R power n is a Hilbert space. See the proof. So for the Hilbert space, we want three elements. We are getting x, y, z belongs to R power n. Once the element in the R power n, compulsory every element is of the form ordered of n tuples. So here we are writing where x is equal to x1, x2, so on xn, comma y is equal to y1, y2, so on yn. Similarly, z is equal to z1, z2, so on z8. Now, first, what is the Hilbert space definition? Hilbert space definition is complete inner product space. So, first we will show that this R power n is inner product space. Later we have to show that the completeness property. So, here inner product space we have to show the following four conditions. Okay, see the first one of inner product space is inner product of x comma x is equal to is greater than or equal to 0. We have to show the first condition, so that see our next lines. Now inner product of first property of inner product space, inner product of x comma x is equal to, so from this inner product of x comma x is equal to, sending that square to this side, root this side, then it becomes root x1 square plus x2 square so on plus xn square whole square. Okay, so square root cancel, remaining the terms are x1 square, x2 square, so on xn square. But here every term is having the square, so that the value is clearly greater than or equal to 0. So that LHS inner product x comma x is greater than or equal to 0. This is our first property, first bit. And next one is inner product of x comma x is equal to 0 if and only if we have to show that x is equal to 0. For this purpose, see inner product of x comma x square is sending that side, what's left these terms. So directly x1 square plus x2 square so on plus xn square is equal to 0. Is equal to 0. If and only if So here addition of n terms is 0, mean to say every term is 0. So that x1 0, x2 0, so on xn 0. So all the x1, x2s are zeros, mean to say here complete x goes to 0. So x is equal to 0, comma 0, comma so on 0. So what we got? Therefore inner product of x comma x is equal to 0 if and only x is equal to 0. This is the inner product space first condition. Clear? So here we have to write like this: x is equal to 0, so on 0. Inner product space first property is this thing. Next, second property of inner product space is inner product of x plus y comma z. We have to show that inner product of x plus y comma z is equal to inner product of x comma z plus inner product of y comma z. So next we have to calculate second property of inner product space conditions. The second property of inner product space is inner product of x plus y comma z. So here we are adding the terms x terms y later comma z1 terms. So how to write it is here I will write first x terms. You already know x1, x2, so on xn. Y terms mean to say y1, y2, so on yn. Next z terms వచ్చేసి z1, z2, so on zn. Right. Now addition of the terms x plus y, so that x1 plus y1, x2 plus y2. Next inner product of x comma y, how it defines? Square root, not square root, x1 into y1 plus x2 into y2 like so on xn into yn. So here x plus y comma z mean to say x1 plus y1 into z1. Like this the inner product is defined. Okay. So here this sentence will be directly x1 plus y1 into our first term z1 plus x2 plus y2 into z2, so on plus xn plus yn into zn. Now here we have to multiply and write the separate terms. x1 into z1 plus y1 into z1 plus x2 into z2 plus y2 into z2, so on plus xn into zn plus yn into zn. Okay. Now here we are writing all the x z terms is in one braces, y z terms is in another braces. So x terms x1 z1 plus x2 z2, so on plus xn zn is in one braces. Next y terms are is in another brace, y1 z1 plus y2 z2, so on plus yn zn. Okay. Now again we have to observe the terms from this x1 y1 plus x2 y2, so on xn yn can be written in terms of the inner product, that is inner product of x comma y. So here x1 z1 is there, so that nothing but the inner product of x comma z. Similarly our second one is inner product of y comma z. So what is the LHS? Inner product of x plus y comma z is equal to inner product of x comma z plus y comma z. This is the second property. Next we have to calculate our third one. For any scalar alpha we have to calculate inner product of alpha x comma y. So what we have to do? Alpha x comma y. So x terms are multiplied with alpha. So later inner product of these two terms mean to say alpha x1 into y1 plus alpha x2 into y2, so on, alpha xn into y1. So this is directly alpha x1 into y1 plus alpha x2 into y2, so on, plus alpha xn into y1. See, this box part only for your understanding purpose. No need to write in the exams. Now, in this all the terms alpha is common, so we have to take it common and write remaining terms x1 y1 plus x2 y2, so on, plus xn yn. Okay. Now again observe this one, x1 y1 plus x2 y2, entire thing is nothing but inner product of x comma y. Same thing, alpha into inner product of x comma y. This is inner product of alpha x comma y is equal to alpha into inner product of x comma y. Next we will show the last property, fourth one of inner product space, that is inner product of x comma y is equal to inner product of y comma x whole bar. Okay. The fourth one, inner product of y comma x whole bar we have to calculate. Nothing but y1 x1 plus y2 x2, so on, plus yn xn whole bar. Now in the next step we have to write this bar value separately to every term. y1 x1 bar plus y2 x2 bar plus so on, plus yn xn bar. Okay, we are separately writing the bar terms. Next, here we are using one since part, that is I will write here, that is x double bar is equal to x. So here we are writing x1 y1 reverse, at that time bar exists, so double bar means to say variable is self, so that x1 y1, and these two write it reverse, then one more bar exists, so that x1, the variable double bar is nothing but a variable, same variable, so that this becomes x1 y1, this becomes x2 y2, so on, then this becomes xn yn. Now this entire thing is nothing but inner product of x comma y. So what we got, inner product of y comma x whole bar is equal to inner product of x comma y. Once these properties are satisfied, then the space is called inner product space. So here, therefore, space is R power n. So R power n is inner product space. Inner product space. Once and also R power n is complete always. So this R power n is complete and inner product space mean to say R power n is Hilbert space. Hence R power n is a Hilbert space. So and here, for suppose this problem, for you will get this problem in the exams for short answer, then this procedure is enough for short answer. In case if you will get this question for long answer, at that time up to inner product space to proof is collected from this problem, and r power n is complete. Completeness you already having in the unit 1. From that you can collect the proof of completeness. That proof also you have to write in the exam. This question comes for long answer. Short answer this completeness proof is not necessary. For long answer, completeness proof also you have to write. So from unit 1, first example of normal space is this one only. From that you will collect the proof and write that proof in place of completeness. So IPS completeness together gives Hilbert space conditions. That's why here I am not giving the completeness proof. Only IPS proof is there. So read the question properly and write the answers. Okay, Nama? Short answer this much is enough. Long answer you can include the completeness proof also. Collect it from unit 1 normal space examples first one. Similarly, now I will explain our second example of C power n. Okay, first one is Euclidean space. Second one is unitary space C power n. So in this C power n also the inner product of the elements are given in the statement. Using that we have to show that C power n is a Hilbert space. C power n is nothing but unitary space. See our second example, unitary space. Unitary space C power n is a Hilbert space if an inner product is defined by inner product of two vectors x comma y is equal to x1 y1 bar, x2 y2 bar plus so on xn yn bar, where x comma y belongs to C power n, not only C power n, and the norm is root of x comma inner product x comma x is equal to x1 x1 bar plus x2 x2 bar so on xn xn bar power 1 by 2. X into x bar is nothing but modulus of x1 square plus modulus of x2 square so on plus modulus of xn square whole power 1 by 2. That entire thing is normals. So here we have to show that the conditions of first inner product space, later completeness. See, for the inner product space, first property is we have to show that inner product of x comma y. Inner product of x comma x is greater than or equal to 0 for this. Let x comma y belongs to C power n. Here not only two variables, no, three we want to. So x comma y comma z belongs to C power n. Where x is equal to order of n to same thing x1 x2 so on xn, y is equal to y1 y2 so on yn, and z is equal to z1 z2 so on zn. Now using this, so inner product of two variables is defined as x1 into y1 bar, second variable bar, plus x2 into y2 bar, so on. Now, first property, for this inner product of x comma x is equal to, so here inner product of x comma x is equal to, if you are observing inner product both sides, root 2 power 1 by 2 same cancelled, so write directly remaining terms, that is x1, this one left, this one is nothing but this thing, so directly we are writing here x1 square plus x2 square so on plus xn square. So every term is having the square and the modulus, so that all these terms are clearly greater than positives, so that this entire thing is greater than or equal to 0. So therefore, inner product of x comma x is greater than or equal to 0. and inner product of x comma x is equal to 0 implies, here we have to show, and inner product of x comma x is equal to 0 if and only. So directly what we will get, inner product of x comma x, this square is cancelled on both sides, so left out the terms are x1 bar plus x2 bar. That one is nothing but directly this one, so we have to write directly x1 square plus x2 square plus so on plus xn square is equal to 0. So here addition of n terms are zeros, so that every term goes to 0. So if and only if x1 is equal to x2 is equal to so on equal to xn, all of those to zeros. So based on this, now, so every term is 0 mean to say here our x term becomes 0. So what is our x term? If and only if write LHS also. LHS is x comma x is equal to 0 if and only x is equal to our RHS. X is nothing but x1, x2, so on. So all the values are goes to zeros. So x is equal to 0, comma 0, comma so on 0. So this is our Hilbert inner product space first property. Next, second one. What is the second one of inner product space? Inner product x plus y comma z. So inner product of x plus y comma z. How to write, addition of the first two terms, inner product with the second term. Inner product with second term means second term, for second term bar exists, so directly it can be written as x1 plus y1 into second term bar exists. Second term z is having the first variable z1, so that z1 bar plus x2 plus y2 into z2 bar plus so on plus xn plus yn into zn bar. Later we have to multiply and write separately. So multiply with z1 bar, x1 z1 bar plus y1 z1 bar plus x2 z2 bar plus y2 z2 bar. Similarly, multiply with last term xn zn bar plus yn zn bar. After multiplying all the x terms, xz terms is in one braces, yz terms are is in another braces. So x terms are x1 z1 bar plus x2 z2 bar plus so on plus xn zn bar plus all the y terms are is in another braces. So y1 z1 bar plus y2 z2 bar plus so on plus yn zn bar. Okay. Now this can be represented is the inner product. So inner product of x comma z. Similarly, second one is y comma z. So our inner product second property is inner product of x plus y comma z is equal to inner product of x comma z plus y comma z. Similarly, we will show the inner product of the third property. Third property, for this purpose, we want one scalar alpha. So what is the third property? Inner product of alpha x comma y is equal to alpha into inner product of x comma y. So for any scalar alpha, inner product of alpha x comma y is equal to, directly multiply and writing alpha x1 into y1 bar alpha xn into yn bar. So if you are observing all the terms are having alpha, so take it common. Alpha into x1 y1 bar plus x2 y2 bar plus xn yn bar. Now alpha into this entire thing is nothing but inner product of x comma y. So third property is inner product of alpha x comma y is equal to alpha into inner product of x comma y. Now the last one for inner product space, that is inner product of y comma x whole bar. Inner product of y comma x whole bar. So y comma x is nothing but y1 x1 bar plus y2 x2 bar plus so on plus yn xn bar whole bar. Okay. Now here we have to write this whole bar separately to every term. Then our next line is x1 y1 x1 bar whole bar plus y2 x2 bar whole bar so on plus yn xn bar whole bar. Okay, right. Now here we are writing this bar separately to every term, that is y1 bar x1 double bar is nothing but x1 plus y2 bar x2 so on plus yn bar xn. Okay. Now write it reverse x1 y1 bar a into b is b into a, so x2 y2 bar plus so on plus xn yn bar. Then this entire thing is gives inner product of x comma y. So inner product of y comma x whole bar is equal to inner product of x comma y. So inner product space 4 conditions are satisfied, so that in this example unitary space C power n is clearly inner product space. So therefore C power n is an inner product space. So you already know in unit 1 C power n is complete, so that also C power n is complete. So complete inner product space is nothing but Hilbert space. So hence C power n is a Hilbert space. This is the second example of Hilbert space. So you will copy the notes from the videos. See, next I would like to explain one result. From that result we'll get the polarization identity. Okay. See our next result. We know that an inner product there is corresponds a norm given by. We know that this thing norm x is equal to square root of inner product x comma x. Then we have the following results. In a real inner product space, elements of inner product x comma y is equal to 1 by 4 into norm x plus y whole square minus norm x minus y whole square. Similarly, in a complex inner product space, elements are complex meaning to say real of inner product x comma y is equal to 1 by 4 of same thing, norm x plus y whole square minus norm x minus y whole square. Next, imaginary of inner product of two elements 1 by 4 of x plus y. Imaginary element is always y, second value. So x plus iy whole square minus x minus iy whole square. Now these together gives the complex variable, so that our next line is real inner product plus imaginary inner product. So real plus imaginary, add these two terms RHS. So 1 by 4 into norm x plus y whole square minus norm x minus y whole square plus imaginary, so I into inner product of this 1 by 4 into norm x plus iy whole square minus norm x minus iy whole square. Real plus imaginary is nothing but a complex number, and here they are sending this 4 to that side, RHS from RHS to LHS, then 4 into this entire element. That entire element is inner product x comma y is equal to, then these terms are as is multiplied with I and y. So 4 into inner product x comma y is equal to norm x plus y whole square minus norm x minus y whole square plus I into norm x plus iy whole square minus I into norm x minus iy whole square. This entire thing gives the polarization identity. See the last line. This gives this is called polarization identity. So with this result, our inner product spaces topic is completed. In the next class, I will start next topic. Okay na?